Pop quiz time. What is the backbone of power management for nearly every modern electronic architecture? Why, yes, I am talking about DC to DC power conversion. Whether it's driving advancements in electric mobility, industrial automation, or supporting the critical infrastructure of telecommunications, medical technology, and consumer electronics, these converters are vital for ensuring precise and efficient power delivery across a whole lot of different applications. And folks, that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Mohammad Mohiuddin from Eaton and I explore the fundamentals of DC to DC conversion, the benefits of the different types of converter architectures, and how technologies like gallium nitride, silicon carbide, traditional silicon MOSFETs, and IGBTs compare when it comes to efficiency, switching speed, and power density. We also investigate key design trade-offs engineers face when selecting power solutions, and look ahead to the future of DC to DC conversion, including AI-optimized power management, miniaturization, modular power systems, and next-generation high-efficiency designs. And before we get started, don't forget to click that link. There you can find even more information about this topic from Eaton. Hi, Mohammed. Thank you so much for joining me.
Thanks for having me, and thanks everyone for joining us today.
Excellent. Okay, so we're talking about the hidden world of DC to DC converters today. But Mohammed, before we dig into the details, what all will we be covering?
We are going to talk about something that's absolutely everywhere in modern electronics, but rarely gets the spotlight, and we are talking about DC to DC converters. From harvesting solar energy to powering data centers to what is inside our smartphone, these converters quietly make modern electronics possible. Today, we will pull back the curtain on this hidden world and talk about why these devices matter and where the technology is headed. We will start with some basics to make sure everyone is on common ground, what DC to DC converters are and why they exist. Then we will zoom out to look at the market and the forces driving growth. After that, we will go inside the converter, which is switches, materials, and topologies, before discussing real world implementations and design considerations. And we'll wrap up with a look at future trends and key takeaways from this presentation.
Excellent. Okay, so let's start at the basics. What exactly is a DC to DC converter, and why do systems need these kind of converters in the first place?
At the most basic level, a DC to DC converter is an electronic circuit that takes one DC voltage and converts it to another. That is essential because different components in the system all want different voltage levels. For example, a system may have a 12-volt battery, but the processor needs 1 volt, sensor needs 3.3 volt, and communication modules need 5 volts. So the DC to DC converters make sure devices gets them and get them cleanly. Another way to think about DC to DC converter is that they act as a buffer between messy real-world power sources and sensitive electronics. Batteries droop, load change suddenly, and inputs aren't always clean, especially in automotive or industrial systems. The converters isolates that chaos and presents predictable, regulated power to the load. They do this using high-speed switching with transistors along with inductors and capacitors that store and release energy. That switching approach is why modern converters are so efficient compared to older linear methods. You will see different types: buck for step down, boost for step up, buck boost for both. And you'll also hear about isolated versus non isolated designs depending on safety and noise requirements.
So, Mohammed, talk to me about the market here. What does that look like?
All right. So, for a market perspective, DC to DC converters are both large and growing. Globally, the market was around $15 billion in 2025, and it is projected to more than double by 2035 with roughly 9% annual growth. In the US alone, we are looking at growth from about $4 billion to $10 billion over the same period. Regionally, Asia Pacific leads in volume today, while North America is the fastest growing region. One important footnote here is that the market size depends heavily on how you define it, whether you are counting ICs, modules, or full power assemblies. So these numbers represent the upper range of industry estimates.
So, what kind of designs are pushing growth in this market? I would imagine that electric mobility designs are making a big impact.
And you are absolutely correct about that. Electric vehicles are one of the biggest growth drivers right now. Every EV uses multiple converters, not just for traction system, but for everything from infotainment to battery management and auxiliary power. Next is renewable energy is another major driver. So DC to DC converters are critical for solar, wind, and battery energy storage, especially when dealing with wide-ranging input voltages. Data center and 5G infrastructure also play a big role. Hyperscale data centers now draw hundreds of megawatt and higher efficiency power conversion directly translate into operating cost savings. And finally, consumer electronics and IoT continue to demand smaller, more efficient power modules. As devices get thinner and smarter, power conversion has to keep up.
Okay, so let's dig into the hardware. What role do electronic switches play in DC to DC converters?
At the heart of every DC to DC converter is the electronic switch. It is the primary power handling element and controls how energy moves from input to the output. As designers push for higher power density, switches are asked to turn on faster, handle more current, and do it with less loss. That is why switching devices are often the first thing revisited when efficiency, EMI, or thermal goals aren't being met. Changing the switch can unlock a new operating space for the entire converter. Every switch choice involves trade offs, namely efficiency versus cost, size versus thermal performance, and this is where material and device technology really matters. When people talk about power electronics getting harder, they're talking often really saying that switching is getting harder. As we push for higher power density, we ask these switches to turn on faster, carry more current, and do it with less loss. That is why the switches are often the first component engineers revisit when efficiency, EMI, or thermal targets aren't being met. If you change the switch, you often unlock a entirely new operating space for the converter.
Mohammed, how do these different switches compare? I'm talking GaN, silicon, silicon carbide, IGBTs.
One thing I want to emphasize is that none of these technologies are better in every case. They are optimized for different trade spaces. Silicon MOSFET, for example, are incredibly mature. Designers know how they behave, supply chains are stable, and the cost structure is very competitive. That is hard to beat. Now, the gallium nitride, on the other hand, is really about enabling new architecture. It is just not higher efficiency, it is higher switching frequency that allows you to shrink inductors, transformers, and capacitors. Silicon carbide plays a different role. It is not trying to beat gallium nitride at low voltage. Instead, it extends efficient switching into voltage ranges where silicon struggles. And IGBT still matter. When you're dealing with megawatt of power, switching speed becomes secondary to ruggedness and sheer current handling capability. So in practice, engineers don't choose gallium nitride or choose silicon. They choose solution that fits voltage level, power range, cooling strategy, and cost targets.
Mohammed, we need to consider efficiency and switching frequency, right? How do these different solutions compare in this regard?
Correct. Efficiency and switching frequency are tightly linked. With silicon MOSFETs, efficiency tends to drop quickly above a few hundred kilohertz due to switching losses. Gallium nitride maintains high efficiency even at much higher frequencies, around 600 kilohertz and beyond, which is why it enables much smaller magnetics. Silicon carbide improves over silicon at higher voltages, but it still doesn't reach gallium nitride performance in high frequency, low to mid voltage designs. This trade off is also why higher frequency isn't automatically better. You save on magnetics, but you increase EMI challenges and layout sensitivity. So designers always have to balance electrical performance with manufacturability.
Let's talk about topologies as well. What kind of topologies are the most common these days?
Traditional hard switch PWM topologies are still very common because they are simple and cost effective. You'll see flybacks in adapters and full bridge designs in telecom and industrial power. Soft switched PWM topologies like phase shifted full bridge improves efficiency by reducing switching losses, especially in 48-volt systems. Now, the resonant converters like the LLC go even further, enabling very high efficiency and power density, which is why they dominate server and chargers today. Another thing to keep in mind is that topologies often persist long after newer options exist. If a design is proven, certified, and reliable, many industries will stick with it for years. What we are seeing now is not a replacement for older topologies, but a layering where resonant and soft switching designs are used, where efficiency and density truly justify the added complexity.
Mohammed, which newer topologies are gaining traction at higher power levels?
We are seeing strong growth in interleaved designs for high current and switched capacitor approaches at the IC level. At higher power, bidirectional topologies like the dual active bridge or DAB are becoming key enabler for EVs, battery storage, and solid state transformers. This shift is largely enabled by gallium nitride and silicon carbide, which makes these complex, high frequency architectures practical.
What does a dual active bridge actually look like in a block diagram level?
At a block diagram level, a dual active bridge or DAB consists of two active bridges, one on the high voltage side and one on the low voltage side, connected through a high frequency transformer, of course. Control logic manages phase shift between the bridges to control power flow, which can move in either direction. You'll also notice protection elements, current sensing, gate drivers, and battery management, all critical for safe, reliable operation. What makes DAB especially interesting is that power flow is controlled digitally through phase shift rather than just duty cycle. That gives designers much finer control and makes it easier to support bidirectional energy flow, which is essential for EVs and battery storage. It is also why DAB pairs so well with digital controllers and real time telemetry.
So, Mohammed, what are some real world applications that rely on DC to DC converters?
DC to DC converters show up across almost every industry. In automotive, they support everything from ADAS to battery management. In healthcare, they power wearables and imaging equipment. In industrial settings, they enable automation, robotics, and predictive maintenance. telecom, retail, aerospace, energy. Once you start looking, it is hard to find modern electronics without some form of DC to DC conversion.
So, Mohammed, when engineers are designing these in, what matters most?
So selection is always application specific. Engineers have to balance efficiency, thermal performance, size, and reliability. Environmental conditions, regulatory compliance, and long term availability also play a big role, especially in industrial and automotive markets. Now, the cost isn't just BOM cost, but total cost of ownership over the product's life. In a constantly evolving environment, flexibility and scalability are key. So the system can stay relevant today and adapt easily to what comes next.
What are the benefits and design challenges here? What all should we keep in mind?
The benefits are clear: high efficiency, precise regulation, isolation, and compact size are all must needed or one point or the other required parameters. The challenges are just as real. The EMI, thermal management, layout sensitivity, and higher cost for advanced materials like the gallium nitride and silicon carbide. So the benefits and the challenges have to be balanced whenever one is looking for the system of DC to DC converters.
All right, so let's look to the future. What kind of innovations are coming down the pike when it comes to these kinds of solutions?
Looking ahead, we are seeing smarter power electronics, AI assisted control, predictive maintenance, and digital telemetry are being standard. We are also seeing more modular designs, wider input ranges, higher frequencies, and tighter integrations. Bidirectional energy flow and energy harvesting will be key for next generation systems.
So, before we go, Muhammad, can you recap your main points for me?
Sure. So the DC to DC converters are foundational to modern electronics. Material innovation and smarter control are driving efficiency and power density. Selection is always application specific, balancing performance, cost, and scalability. The outlook here is strong and continues to evolve, driven by big growth areas like 5G, EVs, IoT, and renewable energy. At the same time, designs are getting smaller, smarter, and more adaptive to meet these growing demands.
Fantastic. Well, Muhammad, I think that's all I have time for today. Thank you so much for joining me.
Thank you very much again for having me. And for the audience, I would say that please visit eaton.com/electronics for a comprehensive view of Eaton Electronics portfolio. And in case if you need any technical or any other assistance, please contact ELX Tech Support at eaton.com.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Eaton. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.